only mode.
Hey guys, good morning, good afternoon, good evening, wherever you are in the world. I'm Mike Aubrey. I'm one of the participants in the UAVC challenge, and with me today we have James Grimsley, who's one of our solar experts, helping out with the cause. And then, as always, Princess Aaliyah. Thanks for being here today. Guys, this is going to be fun today. So solar power is one of those big, it answers one of those big questions a lot of us have, which is how much energy is it going to take for us to stay in the air, and can we get some and make some up along the way? So for that reason, I'm super excited for our talk today, and I hope you guys are too. So before I get started here, I want to just talk to James. Actually, he's an aerospace engineer with 20 years of experience. That's a mixture of both government and contract work. So he brings a wealth of stuff to the table here. He was just going over his deck before we start off here. There's a lot of great stuff in here. We're gonna have fun. But before I give the panel over to him, I wanted to give the forum to Princess Aaliyah, who has some announcements this morning.
Good morning, good afternoon, and good evening. And I love your greeting, Mike. Thank you so
You're
much.
too
I
kind.
think it's great that we could say all of those in one sentence and it'll make sense. Hi, everyone. Thanks again for joining us for the webinar today. I'm excited to learn more about solar powered UAVs and how we can maximize the availability of these to incorporate into our design concepts as well. So I think this is a great opportunity, especially because Kruger is one of those places where you've got lots of sun. You don't have the heavy canopy, so this could definitely become a great option for the teams that are looking at alternative energy solutions for long flights. Well, a couple of things that I just wanted to bring up. The critical design review has been postponed. We are actually merging that with the flight readiness report on June 30th. Once again, we'd like teams to focus more on working and building the UAVs more so than submitting documents to us all the time. So we've cut down on two different areas. So now you only have two more things that you would have to turn in. One, the critical design report with the readiness report on June 30th, and the second one is the flight video. It's not going to be a report anymore, it's just the flight video and the final design report on the 31st of August. And the reason we had to move it to the 31st of August is because the finals are the first week of November. We won't have the time to review everything and give feedback to the teams if you submit them on the 30th of September. So that's the reason we're pushing that 1 month back. But that gives you at least a couple of months to finalize and work on any of the issues that would come up during that period of time. And third, we did have our meeting with General Eusti from Sand Parks, and it was a fantastic meeting. He's really impressed with the challenge, and he's given us a new name. You guys are the think tank. That was impressive. He's like, there's so many people that are coming up with solutions for Kruger, but just seeing the passion from our teams and the ability for them to think so outside of the box. And he's like, a lot of times, solutions come from places you least expect them. And he's like, I like what you guys are doing. This is great. This is like a think tank. And I was like, yes, this is like a think tank, a very powerful think tank. So that was his feedback for us, and he's looking forward to being at the finals as well in Amakala. But having our winning team fly in Kruger, he actually said we can bring maybe a couple of teams to Kruger to fly. So we might extend that to the other two teams that would win as well. So we'll see how that goes. But it would be nice if we could get a handful of our teams to go to Kruger to fly after the final competition. Lastly, we will have a technology conference right after our final competition for 2 days just to talk about the lessons learned, what we could do to improve, and also announcing the next UAV challenge that we're going to hold next year and what that challenge is going to look like. So those are just a few things for me. And James, thank you so much for participating and doing this solar powered unmanned UAV applications in remote areas for us. So the floor is yours.
Oh, well, thank you for having me. This is something that I've been really excited about for several years. I've actually worked in remote-controlled aircraft, hobby aircraft, things like that, my whole life. And this has been somewhat of a holy grail for those of us who work in small electric-powered UAVs. So it's been something I've always been excited about, but I've been lucky enough the past several years to be involved in. So Can you see my slides now?
Can see it.
Okay. Let me go ahead. I'll start with the obviously the disclaimer. Let me see if I can get control of my slides here. Um, Give me just a moment. There we go. Obviously, just this is what the lawyers always make us put on. This is we're not giving away anything that's export controlled or critical information. So everything we're talking about today is either marketing information that either my company or other companies have published, or it's just information that's in the public domain. So there's nothing that we're giving out that's going to get anybody in trouble or anything here. So sort of a quick slide about myself. As Mike said, I've been involved in aerospace for over 20 years. My original degree was in aerospace engineering. Then I went on to graduate school to do mechanical engineering work and research. What happens with most engineers is when we go to industry, especially if we go to the government, we typically have our adjectives amputated, and that happened with me. Even though my degrees were in aerospace engineering and mechanical engineering, the government, at that time the Department of Defense, reclassified me as an electronics engineer. And then they turned around and had me start working on operational flight software for cruise missiles and things like that. So I had sort of an interesting entree into the aerospace industry and the defense industry. Literally got to do a little of everything from embedded flight software to electronics to just the basic vehicle design. So it's a very rich time in my career. Learned a lot, got exposed to a lot of really neat things. I've been involved in the UAV industry for several years, primarily as a state leader. I'm a state chapter president of our AUVSI chapter in Oklahoma, but I'm also involved at the national level in a lot of the advocacy that we're doing right now for the industry to try to get UAS integrated in the national airspace, to try to keep moving the FAA forward on allowing us to fly for commercial applications and things like that. So I've been very active there. I do have a part-time title with one of the major research universities. I'm associate vice president for research, but I'm only quarter-time, so I'm one of the lowest appointed administrators at the university. But it's fun because I get to keep my foot into the research area, keep up with what's going on in all sorts of disciplines. It's a really fun job. And then I'm also the founding and current president of the Unmanned Systems Alliance of Oklahoma, which now is a state chapter of AUVSI. So this is a group that's comprised of industry, academic, a lot of government folks in Oklahoma that are involved in this in different capacities. So it's really an advocacy group for the industry, but it covers more than just the industry side. So why solar-powered flight? And if you've followed what's going on with UAVs, especially small UAVs, internal combustion and gas-powered engines for small aircraft are just not practical. There's a certain size when we really prefer electric propulsion for a lot of reasons. I was involved in RC hobby aircraft my whole life, and I got really excited when we started seeing battery technology get to the point and just the electric motors get to the point where we could have electric-powered RC aircraft. The obvious problem that we run into is that for electric-powered vehicles, the biggest constraint we have are batteries. If we look across the board at all technologies, consumer electronics, computers, we look at everything that's followed Moore's law in terms of getting better in terms of densities, and we can pack more transistors and more circuits into things. And the one thing that hasn't changed greatly is battery technology. We see just immense growth in all sorts of electronics in terms of capacity and speed and everything. But batteries have just barely made improvements over the past few decades. And as a result, battery technology, and in particular battery capacity, is one of the biggest limitations we have in electronics. And it's turned out to be a major limitation for small UAVs. If you've ever flown a small quadcopter or a small UAV, you know that your endurance is limited to sometimes just 20 minutes. If you have a really high-end system and you try to tweak everything out of it, maybe an hour or 2 hours max. But most of the time we're talking 30 minutes or less in terms of endurance. So for a lot of missions and a lot of applications that we want to use small UAVs for, that limited endurance becomes a very problematic issue. It limits how far we can fly, it limits what we can do. It also means that if we're going to go out and do serious work with small UAVs, we have to do something like carry multiple small UAVs with us. We constantly have to put one in the air, have another one getting ready, being charged, so that when the battery dies on the other, we bring it back. So it's a logistics kind of nightmare if we get out and try to do anything serious with a small UAV, especially if we're looking at something that's very important, like some of the humanitarian causes, like wildlife conservation, monitoring poachers, things like that. we would have to have dozens of planes available and constantly putting one in the air and bringing them down. It's a difficult thing. So what we've always wanted to do, if we look at electric power, the ideal sort of the holy grail is how can we generate power from the ambient? How can we generate something on board to power the systems and power propulsion? Solar is sort of the holy grail that we've always wanted to pursue, something that researchers have been interested in for decades, and it's something that's gotten a lot of attention, and also a lot of work has been done in solar-powered UAVs. So we have a quick history. One of the first recognized solar UAVs that flew was in 1974. If you look back at the state of the technology, solar cells weren't all that efficient. In this particular case, Astroflight was actually a small RC company. They had some ties with, I believe, Lockheed at the time. One of the, I believe it's a Lockheed employee, if I remember correctly, actually went on leave and got a contract to develop a small solar-powered airplane. It flew several times until it crashed, I think, on the 28th flight or something. But they used 10% efficient cells, at the time a very innovative battery, but they demonstrated that solar-powered flight was possible. So that was really the first documented time where something was flown like that. Obviously, in the early 70s, and we'll talk a little bit later, the solar cell technology wasn't quite there. The efficiencies weren't there, and so there's some issues that really limited what they did. One of the next really serious efforts to have a solar-powered UAV was in the late 90s. It actually culminated with flight in the late 90s, although the work had been done for several years in advance. And that was by AeroVironment on a NASA-funded project, and I believe they may have had funding from other sources. But they developed a very large vehicle called the Helios, which was something on the order of 230-foot wingspan, a very large airplane. It was using a little bit higher efficiency solar cells, something on the order of 20% efficient. So this was a much more serious attempt. This was a very large aircraft. And then since 1999, we've had quite a few. We've had the Zephyr, which set a record for UAV, solar-powered UAV endurance, flight times, Sky Sailor, Solar Impulse, and several others. The distinction is most of these were designed to be what's called high-altitude long endurance. As you know, satellites are expensive. There's always the issues of putting satellite up in the air. We've always had trouble with launch vehicles and having consistent access to launch vehicles. So many years ago, people started thinking about why not use these solar-powered UAVs that we could fly at a high altitude, maybe 60,000 feet above all the air traffic, and we can keep these potentially in the air for years at a time. We can fly up. We can use what's sort of a dynamic soaring, where in the daytime we can have excess solar power. We can climb an altitude, and then at night when we have no solar power, we can charge some of the excess power we had, use batteries, and we can gradually drop in altitude. So we can constantly take excess solar power, convert it to potential energy, and we can develop a system that can stay above all the storm clouds, stay above air traffic, and stay up at these high altitudes and function almost as a localized satellite. It can do a lot of the functions that a satellite would do. So that was the reason for the things like the Zephyr by Kinetic and some of these others. So the last 20 years or so have been really exciting in solar UAVs, and especially the last 10, I think, have been some of the most remarkable developments. This is a picture of the Helios, and this is typically what we think of when we think of a high altitude, the HALE, the high altitude long endurance plane. This is one of the first, and if you look at it, very large wingspan, very flexible. Unfortunately, the Helios was lost. It came apart during one of the flights several years ago and was lost in the Pacific. It was unable to handle some wind gusts and some storms, but it did demonstrate that almost this near perpetual idea of flight was possible. So this got a lot of people excited, and in my opinion was sort of the seed to a lot of other programs that developed afterwards. Now, solar cells themselves, basically, just as it implies, we just take light energy, energy from the sun, and we convert it to electricity. So there's all types of cell technologies and how that's done. There's monocrystalline, polycrystalline, all different types of materials. There's single junction, multi-junction. There's all different types of technologies that have been developed to do that, all with different limitations and different strengths. So each of these here, these are just some basic images of some lower efficiency cells, and I have some data on a few others that are a little bit higher efficiency and also more advanced a little bit later in the presentation. But basically, the solar cells have been around for a long time. From the early days of the space space industry, when we were putting satellites in orbit, we were using photovoltaic cells, solar cells. Some of the early work goes all the way back into the 1800s. But as we've seen advances in material science, we've seen things like flexible solar cells, very high efficiency solar cells that have different properties that make them more amenable or usable for things like UAVs and flight. So one of the big things that how we characterize sort of the usefulness of a solar cell is the efficiency. You can think of the efficiency in terms of how much of the solar energy, how much of the solar power that we're getting can we convert into usable electricity. So there's actually different types of efficiencies involved in that, but we do come up with an overall efficiency. A lot of things impact that. One of the big things on solar power is the angle of incidence from the sun and how it's hitting the cells. We have things like cosine effect that can determine how efficiently a cell can convert power. So a lot of times if you go out and see a large solar cell farm or a PV farm or something, you'll see the solar cells are on tracking equipment. They're on poles that move around and actually track the sun. So they try to get the panels normal with the sun. Now this is kind of a challenge we have in using them for UAVs, is actually getting all of that incident radiation. But so there's several things. There's the physical orientation and tracking. There's thermal issues that impact efficiency, and quite a few things that add up to an overall efficiency of the cell. But the way we do measure the usefulness and how good a cell is efficiency. This next slide here gives an idea of where we stand with the technology. What's the latest efficiencies we have for research cells? And as you can see, the top right now is somewhere around 44%. Now these cells, not necessarily producible, they're not necessarily usable right now. There's a lot of issues with getting those, on vehicles. But right now, for a UAV, we can put things that are around 30% efficient. So if you look at around the 30% efficient mark on the right-hand side, that gives you an idea of what we have available now that's commercially available that we can use for UAVs. 30% is very, very good. If you think about the original solar UAV from 1974 was using 10% efficient cells. We've tripled the power output for the same amount of area, essentially, in that time. So that's starting to get very practical. When we get above 20%, solar is starting to become very, very useful for UAVs, because it's starting to mean that the weight is not really growing that much, but we're starting to get a lot more power per area that we use for the solar cell. So it's becoming much more practical for flight. Now,
Could you
one of the issues that we have
could you speak to the weight of some of those materials?
Yeah, some of these are very, very lightweight. The big issue is we have really two different types of solar cells. One is we have those that are really kind of the space grade, that are crystalline structures. They're like very thin glass. And that has always historically posed a problem because they're so fragile they break. They're flat, so we have a problem with how do we embed those in a wing without breaking them. If the wing flexes, they break the cells, and also we have to somehow embed it under something that typically filters out light. It causes problems. The big, exciting development over the past few years has been what's called flexible solar cell technology. And these are solar cells that have the consistency of almost a metal foil, incredibly lightweight, weigh almost nothing, literally like an aluminum foil or something. These can adhere to the top of the wing surface of a wing. They're a little bit more ruggedized. They don't require all the protection on top to protect the cells. And so we're not carrying all the additional weight that we would have if we were using something like a space-grade glass-type crystalline cell. So all of the cells are going to be very, very lightweight. What happens is where you get to see weight added is the materials that protect the cells. So if we put something on it, we have to embed it in something. We have to embed it in plastic, or we have to put something on top. That's typically where we see the weight start to be added. So the weight comes from really protection of the cells, not really the cells typically. Okay. If one of the issues with solar cells, this is almost kind of the approach a lot of times is people think that we can just take a solar cell and connect it to something, and we're getting all the power out of it. The solar cell is this magic device that just always is dumping out the maximum power that it can, and that's not true. They're actually very sensitive to how they're operated, and there's a technique called maximum power point tracking, and this is very, very critical for aerospace applications and UAV applications. Basically, a solar cell, if you go back to Physics 101, power is current times voltage. So it's I times V, and that's power. If you look at how a solar cell operates, especially on this slide here, it has, pardon me, it produces different power based upon the load that's on it. So there is this point, if you look at this curve, if we have I on one side and V on the other axis, there's a point when we multiply those together. This is a characteristic of how a solar cell operates with different loads. There's a point where we get the maximum power out of it, where I times V is maximized. And that's called the maximum power point of the solar cell. So what we have to do is, to get the most energy out of a solar cell, we have to do some sort of electronic magic work on it where we operate it at a condition that's always kept at that load where it has the maximum power output. So that's one of the key things for UAVs, is that we have to do the power conditioning of the solar cell in order to get the most power out of it. If we don't do that, what happens is we can lose 80% of the power sometimes. We can lose a significant amount of the available power by not operating the solar cell properly, or the solar panels if we have an array of solar cells all put together. If we don't operate it properly, operate it at the right load condition, it can impact how much power is available. This is incredibly critical for UAVs, and it's something that a lot of times even experienced designers don't think about. They think that they can take the cells, connect it to the powertrain or to the power bus on a UAV, and it's going to work magically, and that's not the case. So it has to be a little bit of work there. So if we look at solar-powered UAVs, the holy grail, what people really want to do and get excited about is eternal flight. That's what's driven things like the high-altitude, long-endurance vehicles, where they can stay up theoretically for 5 years, many, many years. For all practical purposes, they can fly eternally, have perpetual flight. We really have two different scenarios. One is that we design the vehicle so that it can do that. It either has excess solar power that it can convert to potential energy, it has onboard batteries it can charge, we can have that extra energy available at night when there is no solar power. We can design something that is, for all practical purposes, perpetually powered. Or we can have something that's really not, that's sort of solar augmented, but for some reason or another, it's not going to be capable of powered flight eternally. So those are the two types of scenarios. The tail vehicles, like I mentioned, those are typically the ones that we want to do fly for many years at a time, or eternally. The others are solar augmented. Those are typically the ones that we're going to operate at lower altitudes. And really, the ones that we would look at for many remote applications, like some of the humanitarian purposes we're talking about now, are really the ones that don't fly forever, but they're going to fly very, very well for like an entire day, or perhaps an entire day and then a few hours into the night. Those are the scenarios that are going to be more practical that we'll see for the applications like we're talking about here. So even though the solar power is available, it's still not practical to get away from batteries. We still have clouds. We have the issue of not being oriented with the sun. So even a solar-powered UAV is going to have different levels of solar power available to it. So it's not practical to design something that doesn't have a backup battery. What happens is if we lose sun temporarily, if the solar power drops, and we don't have some sort of backup, then we lose the electronics, we lose propulsion. So pretty much all solar-powered UAVs have battery backups. Now, in vehicle design in general, the big trade-off, the big challenge for us in designing any airplane, whether it's manned, unmanned, solar-powered, non-solar-powered, it's always a weight trade-off. Aerospace engineering is this massive exercise of trying to work with conflicting constraints. We always want to add things, we need payloads, we need things on the airplane, but we're always trying to trade off weight. So, and that's no different with a solar-powered UAV with batteries. We're always having to do that trade-off. We only want to put only enough battery that we need on it. We don't want to add too much weight. So basically the trade-off in the sizing and the weight can be very, very challenging, and it's still one of the most difficult things even for solar-powered UAV is how do we handle that battery part. Now, one of the records thus far, pardon me, I'm just getting over an Oklahoma cold. I apologize for the cough there. One of the examples of a really long flight was the Zephyr by Kinetic. What we've seen a lot of times is a lot of these vehicles, it's not so much as long as it can fly, it's just that people get tired of flying it over 2 or 3 weeks, and the ground crews get tired, or I don't think we've fully seen anything fly to the full potential limit yet because of just people get tired of it. And once we demonstrate a certain point, people say, okay, that's good enough, let's just bring it down. The Zephyr record, the official record, is something like 336 hours back a few years ago. But a lot of these systems, the HALE vehicles, are being designed like the DARPA Vulture program. Some of those were designed where the vehicle would stay in the air at least 5 years to serve the function of a satellite. The Zephyr, even though it's a fairly big airplane, something I believe it's over 100-foot wingspan, fairly good sized wingspan, it still has a very small payload on the order of something like 5 pounds, I think. So these are big vehicles, but they don't have very, very big payloads. These are optimized to use solar power to stay up for a long, long time. And like I said, basically the big challenge is if we want to sit there for 5 years, what do we do at night? And what we can do is if we're overpowered, if we have more solar power available in the day, we charge batteries, and then we also use that to climb in altitude, and then at night we can gradually drop in altitude. So a lot of the hail vehicles, they don't stay at a constant altitude. What happens is in the day and night, they're constantly climbing and dropping at night. So they're changing altitude all the time, and that's one of the ways that they store power is they store it by potential energy in climbing in altitude. But they typically have backup batteries, so at night what happens is as they're drawing battery power, they're throttling down and they're gradually dropping. These things typically have aspect ratios that look like a sailplane, and I'll talk a little bit about that in terms of what's an ideal design for a solar-powered plane. So they fly efficiently, they low drag, things like that, and they take advantage of that at night to conserve power. Now, one of the things I talked about was early on was the different types of solar cell technologies. And one of the ones that I'm excited about is the flexible solar cell technology. This is a company in Illinois that I've been working with for several years now that's developed a very flexible cell, very, very lightweight cell that has been very useful for solar-powered UAVs. Obviously, the production is still not up where the cost is down. There's still limited production, and with limited production, the cost has not dropped a whole lot yet. But the potential for this for UAVs is going to be incredible. It's satellite grade in terms of efficiencies, which means we're around 30% efficient. A very high number in terms of efficiency, in terms of the amount of power that we're able to convert and make available. But it's very flexible. We can wrap it around the contour of a wing. We can wrap it into, adhere it to an irregular surface. It doesn't take a lot to protect it. Very thin layers of materials to protect it. So the overall weight of this type of solar cell technology is very, very low. It's very, very effective for solar-powered UAVs. And we've worked with microlink devices to take several existing UAVs. This is the AeroVironment Puma, which is about a 13-pound UAV, and we've converted it to a solar-powered augmented. What we found out is that when we take an existing UAV that's not necessarily designed like a sailplane, it's not designed for long endurance, we might be able to double the endurance over just battery power alone, but they're not optimized to get the full exploited benefit of solar because they don't necessarily have the characteristics. But this one, the planes like this, we can take and double the endurance. And similar on the next page, the Raven, which is a much smaller version, it's about a 4 or 5 pound small UAV the military uses, also produced by AeroVironment. We can do things that will double the endurance of that. I mean, it doesn't sound like a lot. You think, well, what's the benefit of doubling the endurance? Doubling the endurance for if you're out in a remote application can mean that you need half as many UAVs that you have to carry with you. So instead of carrying 4 UAVs to accomplish work all day long, you may only need 2. So there, even in doubling or just slight increases in endurance, there's a lot of benefit from that. Also, what happens is these batteries, if you think about if you're working in Africa, you're working in a remote area, having access to the grid to charge batteries is not always easy. One of the biggest challenges is bringing generators around, and it's very inefficient to have a 10 kilowatt gas-powered or diesel-powered generator, and we're charging very small batteries. It's a very horrible, efficient use of fuel and the logistics behind this. So getting batteries charged is difficult. The nice thing about a solar-powered UAV like this one is these set on the ground, and they're charging batteries. So if you're not flying one and it's sitting on the ground in the sun, it's keeping its batteries charged. So there's additional benefit of not only are we extending the endurance of the flight, we're minimizing the logistics required out in the field, which is very, very useful. Now, one of the things pardon me, I talked about was what's the ideal design for a solar-powered plane. Obviously, what we want to do is we want a lightweight plane, a lightweight design. We don't want to do things that add weight. But if we look at nature, if we look at which birds fly most efficiently, we see that certain birds have a very long flight endurance. They can fly for very long distances. They can fly for very efficiently without a lot of energy. They can cover large distances. And typically those birds, if we look at them, they have very long wingspans. They have what's called a high aspect ratio. The aspect ratio of a wing has to do with if we look at sort of the ratio of the width, the wingspan, over sort of the thickness or the chord length. Now, since most wings are irregularly shaped, we convert that where we take the square of the wingspan, divide that by the surface area of the wings. So we define that as the aspect ratio. Uh, Something like a sailplane, like we showed here, that has a very long wingspan, will typically have a long, skinny wingspan, so it's going to have a high aspect ratio. These types of high aspect ratio wings are low drag. Obviously, they're good for because they're soar planes, sailplanes, things like that. That's why we use them for gliders, that configuration gliders. But these are also really good for long endurance solar. If we can keep the weight down, if we can keep from adding a lot of weight because of the solar, these make very, very good candidates. So this is the type of configuration that we like to go to, which is high aspect ratio wings, almost a sailplane. Those are the ones that if you look at a lot of the very successful solar-powered UAVs and solar-powered planes, they start to resemble this type of a design. Now, one of the things that's important is the availability of solar. Solar is not necessarily the answer all over the place. Different parts of the world have different levels of available sunlight. The skies are clear, the length of the day, all sorts of things. So this is a map that a company provided for me that shows the sort of the available energy all around the world. This is a real quick way to look at where are the best places to fly, or best places to harvest solar power. If you look at this, the more red, the more kind of that dark red it gets, the better. So if you look at the western coast of South America, there's some places that are the best in the world. I've actually had a lot of inquiries from some of these areas around the world in terms of solar UAVs, people looking at the technology. The inquiries that I receive around the world typically match the dark red. It's interesting that the number of inquiries match where the best conditions are. But if we look at places like Africa, and then we look at places like Australia, these are very good locations for solar-powered UAVs. The conditions are good. We're going to have high availability of solar power, especially if we get around the equatorial areas where we're going to have more direct sunlight directly on top of the wings and things. These are going to be locations where we're going to get the most benefit and the most application, which ironically are the places where we are looking at some of the humanitarian applications. Probably the greatest need for this technology is also where the greatest available power is and where they're most useful. Obviously, northern Canada, very far north Europe, these are not necessarily great places for solar power. We can still get some solar power, but we're not going to get the levels that we're going to get elsewhere in the world. Pardon. Now this brings me to what my own company is working on. We've obviously worked on converting a lot of solar UAVs. This is something that I've worked on since about 2007 with our engineers. We have taken a lot of what we've learned over the past several years to develop what we consider our first commercial sort of civil use UAV called the Eternus, which is a very high aspect ratio wing. It has that long, skinny wing structure. But we looked at something that has more portability. We started looking at things like Pumas, things that have, they require a lot of logistics. They require some big cases to carry around. And if you look at a lot of remote applications, that just adds a lot of burden. If you're carrying multiple cases that are 6 foot long or bigger, that are heavy, that adds to the logistics burden of accomplishing whatever missions you want to accomplish. So that's just an added difficulty in using the technology. So what we looked at was coming up with a design that met all of the things that we needed for the solar UAV, the high aspect ratio wings, lightweight, etc., but coming up with something that was very disassemblable, something that was storable and what we call man-packable. Ideally, what you would like to have is one person be able to take a plane, assemble it, and fly it. So this is something that's around a 10-foot wingspan. That's sort of the soaring sailplane design, long endurance, but it has a very small footprint. So this is a product right now that we are commercializing. We're actually in the middle of fundraising, doing investment to commercialize this right now. So this is something that we have high hopes for humanitarian purposes. And we can carry a sensor, which a lot of times for things like anti-poaching is important, but we can also carry a non-sensor payload, which if you look at areas like Africa and other areas, moving a tissue sample around, someone is ill and we need to figure out what's wrong. Moving a tissue sample can be very challenging to get it to a hospital a couple hundred miles away, or moving small amounts of medicine, small parts, things like that. Those are big challenges. So we're seeing a lot of humanitarian applications for this particular product that really, really excite us at this point. So in summary, there's a lot of promise for solar-powered UAVs. A lot of areas in the world where we have some of the biggest humanitarian challenges are those areas in the world where we have minimal infrastructure, the roads may not be great, We don't have access to a consistent power grid, those types of things. So there's a lot of benefits of a solar-powered UAV that addresses a lot of that. The solar cell efficiencies, which is the big driver, making it even better for UAV applications. The efficiencies are increasing, kind of gradually ratcheting up. But the big thing is that the price is dropping. As the price drops, it becomes more and more available, and then it's become more readily available for different types of applications and users. So we're seeing that as the demand increases, the price is dropping, and I think that's going to continue in the future. And so obviously, more efficient UAV designs, we're seeing a lot of multifunctional designs and optimization going on. So this means that the UAV performance is getting much better. So we're getting some really interesting designs now, and this is driving some of the design science on UAVs in some really interesting ways. So this is something that I'm very excited about. I think we're still in the infancy of how we're seeing solar power being used for UAVs. We're still at the very early stages, and I think in the next 10 years we're going to see some remarkable developments in terms of solar-powered UAVs and the solar-powered small aircraft. So with that, I have that's the end of my slides. Definitely willing to answer any questions that you might have.
Wonderful. Thank you so much, James. This is
Yes,
very
sir.
insightful. So, guys, at this point, if you have questions, some of you have been chatting with us as we go. For those of you who aren't as familiar with GoToMeeting, on the right side of the screen, by default, there's actually a chat box there. If you guys have questions, shoot it our way, and we'll get them in the queue.
So I've got a
Looking at
question
one, let me
actually.
see.
Sure.
Go ahead.
Go ahead.
I was going to actually ask about how do you determine the weight of the solar cells and how efficient they are, because of course everything you carry on a UAV is going to affect the endurance of it. So how do you determine that? So I know you have the lightweight, you discussed the microlink lightweight UAVs, but even with something that's lightweight and you're spreading it across a 12-foot wood span or a 10-foot, how do we calculate the benefit of the solar power compared to the endurance of it as well?
Okay. That's a good question. Actually, what we do is it's almost like a battery where we look at things like energy density. There are ways that we measure a battery, like a lithium polymer battery has a better energy density than a NiCad battery, a nickel cadmium. And what that means is for the weight of the lithium polymer, we get more power, more energy out of it. It can store more energy and have it available versus lower efficiency type or lower density type batteries. And it's the same thing with the solar cells. We can convert that into the solar cells themselves. They have virtually no thickness. So density is not really, we don't measure the density in the same way. We almost look at it as just area, where we look at how much energy per area. So that's really how we define it. There's a lot of things that come into play when you're adding solar cells. So if we just look at just the solar cell efficiency and weight there, that's not a good measure. We have to look at several things. One is what types of materials do we have to put on top of the solar cell to protect us. If we're not careful, we can pick fragile cells that require a lot of material to protect the cell, to keep it from being damaged or broken. That can add a lot of weight. Another thing also, and this is a common problem with UAV design, is we're very poor sometimes when we design it at estimating wire weight. So if we don't string the cells together correctly, we can end up with a lot of wire and a lot of connections. That adds weight. So really what we want to do is we want to find those types of solar cells that don't require as much material protection. We don't have to necessarily embed it below real deep levels of materials in the wing. So the basic number we start with is just the area, where we look at how much power per area. And then we try to estimate how much is it going to cost per maybe square centimeter or square inch. We can come up with numbers where we factor in things like the protection, if we have to put some sort of a film on top of it or some sort of material on top of it. So we compare it almost in the same ways that we do a battery in terms of how much power we're going to get out versus weight. It's still a little bit of a challenge. It's not necessarily easy up front. We have to factor in electronics. We have to add the electronics to do things like maximum power point tracking. So that's an additional weight on top of the solar cells that we have to add. So that answer the question? Okay.
Yes, thank you.
So,
Sure. Let me see if I can scroll. I'm having trouble seeing all the questions. Let me see if I can. Go ahead.
read
Mike,
Venkatesh has a pretty technical one. I don't know if if you want to get into this level of detail. His question was, what do you look for when designing an optimized line regulator over and under voltage for a solar cell?
That's actually a good question because typically, if you look at what's going on with maximum power point tracking, sort of like DC to DC regulators and matching going on there. So what we have to look at is we have to look at techniques and circuits that don't add a lot of weight. What typically adds weight is if we're doing any sort of switching where we have to have big inductors. Inductors can be noisy, but they can also be heavy. A lot of times, we want to put shielding on it for a variety of reasons. And pardon me, it's a little bit of a design challenge because what we want to do is we want to be able to. We don't we don't have the liberty to over design. We can't oversize things because it just adds unnecessary weight. So it really depends on the technique that you're using to do things like maximum power point tracking. There's different software techniques you can use. There's different hardware designs and circuit designs you can do. It really depends. But a lot of times it comes down to component sizing, the types of components. That really can drive the weight. And if you're not careful, it can negate some of the benefits of the solar cell technology. If your circuitry ends up being super heavy, then you've negated a lot of the benefit that you get from the solar.
So would a good way to summarize that be that you really aren't doing anything that would be unconventional here? All you're doing is just trying to see which of the existing techniques are the lightest.
Exactly, exactly. And sometimes we may want to give up a little efficiency if it'll save us a whole lot of weight. And so that trade-off is constant. We're constantly fighting that trade-off.
Okay, Venkatesh, hopefully that answers your question. Shoot us another line here if we aren't quite on track there. Here's a question from Sarah Myers, just a general question about using UAVs for combating poaching. Sarah has a question, where is the best place to find info and how and where UAVs are currently being used to combat poaching? So welcome, Sarah. Princess Aaliyah, do you want to field that about
Yeah,
where
sure,
someone could
sure.
go to learn
I could
more?
definitely do that. Now, there are several organizations that are using UAVs for observation purposes, for surveys of, collecting the data of orangutans or other types of animals. But there are actually no organizations that I know of, at least, that are effectively and efficiently using UAVs for counter poaching. So that's where the challenge comes in. One of the reasons why we started the challenge is because there are no UAVs right now that are geared towards counter poaching purposes. The key we have to understand when we look at a counter poaching UAV is you can't change the way a ranger functions or the operations team in the field function. You have to be able to give them actionable information. So we started the challenge to actually be able to give the rangers the same type of commands they get right now to say, okay, where are these poachers? How many are there? What types of weapons are they carrying? And how far are they from the different types of animals? So that's the purpose of our challenge, is to actually create these counter poaching UAVs that would be used in the field. But as of right now, there are no counter poaching UAVs being used for counter poaching purposes. Yes, they are being used to test an environment and to see if it's possible, but nothing that is able to process all the information on board, such as what the focus of the challenge is, to focus on the embedded systems and the processing of the information the UAV collects as it flies over an area and gives the rangers or the operations headquarters a message saying, okay, you need to send rangers to this location because in 20 minutes this animal will be poached. I hope that answers your question, Sarah.
And if Sarah have not let us know, there are just some various TED Talks and various other people that have mentioned the possibilities of UAVs. There's definitely some resources out there. But yeah, one of the things we think is pretty special here, as Princess Leah said, is what we're doing here is we are actually trying to be that resource.
This
Uh,
one thing I'd like to add, if I could, to that is all over the world, the ability to legally fly is really different all over the planet. The United States is the most difficult place to operate a UAV right now because our airspace is so heavily regulated. It's a very safe airspace system, but it's also very difficult to fly and get permissions. But that's different in all over the world. Some countries it's much easier to fly. Some have virtually no restrictions, and some have limited restrictions, and then some places are very heavily restricted also. So.
So I have a question about, sorry, is there another question?
no, you're good. Go
Okay.
ahead.
So I have a question about, so one of the things that we're looking at for counter poaching purposes is that most of the activity occurs in the evening and the late night. How could we benefit from solar powered UAVs in a scenario where we're really doing our missions during the
Basically,
nighttime.
yeah, there's several ways you could do that. One is that you use something in combination with the solar power. So fuel cell technology is another candidate for operating UAVs, and one potential thing is to use solar during the day and then something like a fuel cell at night. The problem with fuel cells is typically they're like rocket engines. You start them and you can't hardly regulate or stop them. So you're pretty much producing power whether you're using it or not. So that's always been an issue there. We can still design UAVs very efficiently so that when we fly during the daytime, we are taking advantage of things like altitude for storing power, but also minimize, pardon me, the need to draw battery power during the daytime, so we conserve battery power so that it could fly at night. So we could design the solar UAVs that at the nighttime, during night, they still fly the same as a battery-powered UAV would, but during the daytime, we're not using any of that battery power. And then the other thing is just the logistics. Even if we're flying at night, some of these remote areas, it's difficult to keep batteries charged because of lack
Right.
of access to the grid and things. And so having even a solar power plane then keeps the batteries charged in the daytime. We can keep it topped off so that even when we do fly at night, it's a little bit of a challenge. So I think we'll continue to monitor battery technology. There's some promising gradual improvements in energy densities of batteries that are going to help us at night. Uh, Pardon me. And then there is fuel cell technology where we're looking at having to carry maybe compressed hydrogen and things like that that we could potentially use at night.
Kavitha-san. I just totally butchered your name. I'm sorry.
Hi, remember, he
um,
goes by Covey.
Kavi. Well,
Yes.
hello. Has a question around the impact of cloudy days on the efficiency of solar cells. And then a secondary question, can you explain more about amorphous solar panels with respect to current and voltage produced? Um,
Yes, pardon me, I'm not a materials guy, so I'll preface everything I say about that. Clouds, it's surprisingly, you get more solar power. It depends on really kind of the how the solar cells harvest in terms of the spectrums that they use and things like that. What's the wavelengths that they're really responding to. So my experience has been that even on cloudy days, we still get pretty good performance. I've flown some of the vehicles that we've done, and it's very overcast. And surprisingly enough, we're still getting useful solar power, not maybe half as much or less, but you still get, even on a cloudy day, you're still going to get some solar power. It's just not going to be peak. It'll be 50% or less. Now, regarding I'm definitely not a solar cell expert. I have to preface everything I say with I'm a vehicle designer who's just learned a little bit about solar cells. So things like amorphous solar cells and some of the other things, I'm not really an expert on those things, so I probably couldn't answer very, very well. There are a lot of different tricks that are being used out there to try to harvest the maximum amount of light. Trying to do things where you get the most coming through an aperture and things. So there's optical things going on, concentrating
mhm.
the solar light, things like that. So, but on the material side, I'm definitely not an expert, so I probably couldn't answer that very well.
Yeah, a follow-up question that do you have a favorite kind of resource to kind of stay appraised of what's coming out? You mentioned that there's going to be a lot of rapid change coming. Like with amorphous technology, I mean, I think the days of the flat, just conventional solar panel might be
Right.
going away.
Right.
Where do you go to keep up to date?
It's very difficult because it's happening all across the board. You could stay busy full time just watching the research literature just on solar cell and photovoltaic technology and stuff. I try to just keep up with the industry news, especially on the
Mhm.
electronics side. Um, we in aerospace we have this sort of beneficial relationship with consumer electronics, and especially with small UAVs. We look for these opportunities when people are going to put a high efficiency solar cell on their iPad because that's going to make things a lot cheaper. It's going to improve the yields. Quality of manufacturing goes up. Same thing with battery technology. So small UAVs, we benefit from that. So I watch just normal trade publications, and then we do work with some of the solar cell manufacturers. So we're sort of have a little bit of an inside track in terms of what the industry is predicting and where the state of the art is right now.
Hmm.
For small
Okay.
UAVs, James,
Mm-hmm.
I know you mentioned the Zephyr,
Mm-hmm.
which is 100-foot wingspan or
Right.
something. But if we're
Right.
looking at small UAVs, maybe 10 feet or
Mm-hmm.
12 feet, maybe even 15 feet, What kind of, I guess, what kind of endurance can we get from solar panels on a wingspan of that size, approximately, on a nice sunny
Well,
day?
well, what we like to use is the term near perpetual. So if you size it right, you can fly all day long. If your vehicle is very lightweight and it's very efficient, has the soar plane characteristics, the high aspect ratio wings and stuff. The issue is that there's a certain time of day. The sun angles are very important. So there's when the sun is first coming up, the sun is almost horizontal to the wings, and so you're
Mhm.
not really getting that light on the solar cells. So there's a little period in the morning when it's not very useful. You're not harvesting or using very much light. But then there's a point at 9 or 10 o'clock in the morning when the sun starts to get at a certain inclination when you're starting to get more direct solar power. So it really depends on the seasons, the location, but you can get several hours a day of really good strong sunlight. And the same thing in the evening. There's a certain point when the sun drops down when you're almost parallel again to the wings, so that inclination is an issue. And then there's also the issue of flying. You're not always oriented with the UAV toward the sun. So, sometimes it can be almost a mission planning exercise just to make sure that you're constantly either facing in the right way or you're oriented in the right way that you can harvest the maximum amount of solar power.
Have you worked with any UAVs where the UAV can detect which is the best position to fly in to maximize the sun rays?
It's possible. I've never worked in any situation where it sort of adjusted the path. That's a very interesting point that I've actually been talking with researchers about because we can definitely track. We can orient and do a physical tracking in flight because we can detect when we're getting enough solar panels. So we could orient the plane either in a pattern or direction or something and orient that. You do have the situation where if you're flying in a closed area, you may be optimal one direction, but then you have to try and fly back at some point. So you may be unoptimal the other way. But we've talked about that. There's research going on to find ways where you use atmospheric conditions, where you detect the thermal, uh, basically an updraft. So if you take advantage of the thermal conditions, you can constantly maybe stay in the air and take advantage of that to extend flight. Birds do that all the time. If you ever see birds that are soaring a long time, they'll find these thermal drafts that carry them aloft even higher. So there has been work on that, on detecting the thermal sort of these areas where they can do the dynamic soaring and take advantage of the atmospheric effects. The light is possible. I'm personally not aware of anybody that's done it, but I find it a very intriguing challenge that at some point we would like to
Hey, that sounds like a good plan next time for our challenge then. A requirement for the next challenge. Maximize solar panel use.
Hmm.
Mike, did you have any questions? I know I
Uh,
see
there,
your brain spinning.
do.
the updraft one, you're rocking my brain with that one. That's a really interesting, creative idea. Venkatesh actually has a follow-up question.
Sure.
Um, uh, this is actually, I guess, a matter of preference. I imagine the answer will probably be a little bit of both. But he said, would it be more efficient to create a low amp draw motor like Halibach? Oh, let me go back. A low amp motor like a Halibach array motor and use it with a large diameter prop, or would it be better if we just reduce the weight and optimize on design?
Um, the air vehicle design is always this exercise of conflicting constraints, and so
Yep.
typically what happens is we end up with the best designs, or we have little improvements all the way around, but it contributes to an overall better design. Um, Everything comes at a cost. There's always the cost of weight and power, and trading that off, and not only weight and power, but just the monetary cost. Sometimes things can be super expensive, become prohibitive because for a small UAV. Um, when we first started with small UAVs, for decades, small aircraft were not considered a serious research issue. The only work that happened with small aircraft for decades, for almost the entire 20th century, was in the hobby industry. Researchers didn't care about anything unless it could carry a person. The Wright brothers actually set the lower end of the scale for manned aircraft, and so that's really the serious aerospace researchers always looked at manned aircraft. So the hobby stuff was in the domain of sort of what we didn't consider really serious in the sciences. As a result, what would happen is things like propellers were not necessarily efficiently designed. When you go down to smaller scales, those of us who are aerospace engineers know that basically a lot of the physics change. A lot of the things in fluid flow and airflow, things change when we get to smaller scales. Reynolds numbers are different, things like that. So what happened was hobbyists were taking propellers of big aircraft and just scaling them down. And what we found out is when we started seriously attacking a small UAS and small vehicle design in the sciences, engineering sciences, and research and things like that, we started realizing that we were using a lot of very inefficient designs. So that there was a big push for a few years to really look at how do we design very efficient small propellers, how do we get more efficient motors, all of these things like that. So to kind of answer the question, in general, it's better to look at a total integrated design where we're trying to optimize with all the constraints. We can always make improvements in an area, but we always have to gauge that in terms of what are the other costs and what's the impact going to be on the overall system.
I'm going to combine two questions for the next one, and then we'll probably call it. Oh, we just got another question too. So maybe okay, we got time for three more questions. So Raj and Marcel actually had similar questions that came at the same time,
Okay.
basically asking, are we? Actually, let me paraphrase both. Do you see a lot of people using solar power to power the actual motor, or do you see people using it instead to power the smaller electronics? Is there a reason to do one or the other? What's your preference?
Um, I probably see more people wanting to power the powertrain, the props, and motors, and things like that, in an integrated solution. Where it comes useful for augmented power is suppose you have a gas-powered vehicle, that's 100 pounds or 200 pounds, something like that, and you want to add a lot of sensors to it, and you don't want to have to add a lot of wiring. You want to put localized sensors. A lot of times you can add solar cells to do those just power sensors that you may have augmented and added. But typically people are looking at more of an integrated, let's provide power for propulsion as well as sensors both.
Okay. All right, guys. So the answer is yeah. People do more of the powering of the motor. Uh, Actually, it was interesting. That one just strikes me too, because my group was talking about last night using solar panels actually to power the camera instead
Mm-hmm.
of worrying about powering the motor, just because of the power is a lot more in line. Like the voltage and current requirements for the camera are far better than what we have for our for the motors. You have to really vamp up that current, and it just dumps in. I just can't see solar power really helping with the kind of speeds we want to achieve, at least
Right.
for our bird. But we could use it to.
What we see, that's
Yeah.
actually a good question because what we see a lot of times is we end up oversizing batteries because of the peak demand on the batteries.
Mhm.
And if we can lower that peak demand, because every once in a while we're going to have the motor full RPM and everything happen at once, and that's typically how we size the batteries to handle those situations, even though that's not what's going on the entire time during flight. So a lot of times using things like solar cells or other things, if we can do things that reduce the peak demand, it changes how we can size the batteries, which can be a big impact on the design itself.
Hey, sorry guys, I know we have a couple of minutes, but can we get Mark Moore? He's doing our webinar next week. I want him to quickly give like a couple of sentence summary of what next week's webinar is on, because I think it's very useful for the teams, and being able to understand what he's going to be doing his webinar on. Mark, hi, can you hear us?
Can you hear me? I can hear you.
Yes, we can hear you. Hi, Mark.
Hi, how you doing?
Good. How
Great,
are you?
great lecture. I appreciate being able to watch and
Thank you
learn.
for watching. So can you kind of do a quick overview of your webinar for next week and how important it is for our teams to actually be on that webinar as well?
Yeah, certainly. So I'm going to be talking about a tool that we've developed at NASA. I've been at NASA 30 years doing conceptual design the entire time, and my specialty area is unmanned aerial vehicles and smaller vertical lift platforms. So we developed this really neat parametric geometry tool, which we've open sourced so that anyone can get it for free. And I'm going to be showcasing how we use that rapid geometry builder to develop UAV concepts and how to then send those geometric models directly to lower order and higher order analysis, such as aerodynamic analysis, and be able to use this core geometry to get to all sorts of different abilities to understand how your UAV will perform.
Wow. I think that's going to be a great tool for the teams, especially if they're able to use it. Now, I know I would recommend that if you guys can download this before the webinar next week. What is that website, Mark?
It's www.openvsp.org, O-R-G. This
Okay,
is free
let
software,
me type it in.
which is incredibly powerful and should help you out.
So it's vsp.org.
Open
Oh,
VSP.
open. Okay.
VSP stands for Vehicle Sketchpad. And one of the other things, besides downloading the program, you may want to go into the Hangar, which is where people share their different OpenVSP models, so you can get a bunch of different free geometries that people have already developed.
Awesome. Well, thank you so much, Mark, for giving us that quick overview. We're going to go back to James now, but we'll see you next week, Mark.
Wonderful, thank you.
Thank you
Thank
for
you.
participating
I'm
today as
looking forward to
well.
it.
All right, James. Mike, do you have any questions that you want to end with, or?
No, I think I'm writing this final one to Kavi about. He had a question about how efficient is our solar panels with artificial light. And
Mhm.
actually, let's see, James, you correct me if I'm wrong here. So, Kavi, your efficiency will be the same, but the difference is with artificial light, the available energy from them is actually quite less because they're limiting the spectrum it's producing from, and then frequently artificial lights they oscillate the light to minimize the energy there too. So, just your returns on going after artificial light sources will be much less. How'd I do, James?
Yeah, that's actually very, very good. And in fact, we've had some challenges in trying to simulate that using halogen lights. We've even overheated solar cells before they get too hot doing that. But yeah, not having that full spectrum, it's fluorescent lights like this room, it's just not the same. So it's not nearly as good.
But they definitely do it though. Your calculator, like your little TI calculators, they operate that way. So it's
Absolutely.
definitely done.
Yeah, to get full spectrum to really simulate full solar light, it's difficult. We've used combinations of fluorescent and halogen, a lot of different things all at the same time. But you can get light. It's just going to be a lot lower typically in terms of the amount of power available. Or you can get power. I'm sorry.
All right.
Okay, I guess we'll end on that. I mean, James, thanks so much for being involved, and thank you for putting your contact info up there too around the kind of what comes next from this. As you guys have questions, definitely reach out. Um, yeah, that was cool, James. It was so
Yes.
timely for my team. So thank you so much
Okay, great.
for taking the time to be with us today,
Appreciate the
and
question.
for everyone else around the world. We'll see you guys on the next one.
Yeah, looking forward to it. Thanks again, James, for
Thanks.
a great webinar today, and we'll keep in touch. We might do another one maybe like June, July-ish,
Okay.
as teams get closer to looking into alternative solutions for their battery packs. All right.
Thank you for having me. Thank you.
All right.
Very
Thank you
Cool.
guys. You have a good one.
All right, guys, take care.
All right.
Bye.
Cheers.